We have Daniil Dmitriev from ETH, who is going to discuss the Lovasz number of random circulant graph. Please go ahead.
Yes, yes, thanks a lot for coming. Thanks a lot for inviting. It's always great to be at this beautiful place. So I'll talk about our recent work, Lovasz number of random circulant graphs. This is joint work with Afonso, Yaroslav, Ulis, Anastasia, and Tim. I'll start with discussing what are different families of random graphs we are considering, discuss the problem of de-randomization, then I'll introduce the Lovasz number, and show our main theorem with some of the proof sketch. So we will consider graphs, undirected graphs in particular. And for this talk, I'll denote by I tilde j, that the node I is connected to node j. For example, in this graph, 1 is connected to 2, and by this, 1 is not connected to 9. And the independent set is like a basic quantity property in the graph, which is the set of vertices so that there is no edge between any pair of nodes. So here, 2, 5, 6, and 8, they form an independent set. Independence number is the fundamental quantity of the graphs, like studied in the graph theory, which is the size of the largest independent set. And I believe for this graph, the answer, the independence number is 4, because you cannot find an independent set of size 5. But in general, it's in P hard to compute. So there's no better way than just to go over all the subset of vertices and manually check whether there is an edge between any pair or not. Okay, so I'll come back to independence number. So we'll be studying the random graphs, and let's start with the most famous model of random graphs, which is Erdős-Rényi random graph, which parameterized by number of vertices n, and the probability of the edge p, which is for this talk I'll just fix to 1/2. And to sample Erdős-Rényi random graph, I just go over all the pairs of nodes, and I just kind of toss a coin and see whether there is an edge or not. So for example, between 1 and 2 there's no edge, 1 and 3 there is an edge, 1 and 4 no edge, and I continue like this for the whole graph. And each time, so this is how I sample a graph, and each time I check whether there is an edge between two nodes, it's like I kind of use one random bit, and I toss a coin. So the random graphs, they are prevalent in mathematics. For example, they can be used to prove certain results in combinatorics. There is so Erdős showed in 1947 that there exists a graph on n vertices such that it does not contain large structures in it. In particular, the independence number of the graph and the independence number of the complement of the graph are both small. So for n vertices, they are both at most 2 log n. So independence of the complement is called clique number. However, up to this date, it's still an open question to show an explicit construction of such graph. But we know it exists because we know if we sample a random graph, then with positive probability, it will satisfy this property. However, there's no efficient way to just write down the edges of the graph and to prove that it indeed does not have large independence and clique number. So I like this quote by theoretical computer scientist Avi Wigderson that solving this open question is essentially finding hay in the haystack. Right, because not only we know that with positive probability, the random graph will satisfy this, but even with high probability, a random graph satisfies. So if you sample a random graph, it almost sure, like with high probability, it will satisfy, it will be like a good graph without a large independence and clique number. So you can imagine you have a haystack of graphs, and like basically it's almost all graphs, they are good graphs. However, if you sample a graph, you don't know a priori, you cannot efficiently check whether it's indeed like some general looking graph, or maybe just unlucky and you end up with some very special graph, for example, like a star graph here, which definitely has a very large independence number. So how like this open question is open for like 80 years. One way how we could maybe tackle it is if we would have indeed a deterministic graph, a deterministic way to construct for given n a graph, together with the proof that it is indeed kind of general looking. So like, in a sense, random in some sense, but it is deterministic. And we can zoom into this question in terms of degree of randomness. So here I put, on the left I put the Erdős-Rényi graph, so which required many random bits to generate it. And actually we have a candidate for deterministic graph, which will close to solve the previous problem, which is a Paley graph. So this is a deterministic graph and comes from number theory. And it's believed that it has some certain pseudo-random properties. So it will kind of behave like a Erdős-Rényi graph in some sense. However, like to tell something about Paley graph is quite complicated because, okay, for me at least, because it relies a lot on the number theory. Yeah, like, and basically, maybe if you would have like youth in number theory, that would be a good topic to talk about Paley graphs. But in the youth in high dimensions, we should talk about some random high-dimensional object, which is our focus. So something in the, but it's something in the middle between Erdős-Rényi graph and the Paley graph, which is random circulant graphs. So these are still random graphs, but you can see on the picture that they are very structured. So they kind of look like a Paley graph. They don't look arbitrarily, like the edges are not arbitrarily shuffled, but it's still random. Okay, so let me now introduce how to sample a random circulant graph. So I will denote it by RCG, and n is number of vertices. And essentially, I start with the same way as before. So I start with an empty graph. And now I look for neighbors of vertex 1. And I just check for the edge between 1 and 2. I toss a coin. Maybe there is no edge. 1 and 3, there is an edge. 1 and 4, there is an edge. 1 and 5, no edge. But at this point, I stop. And that's the only randomness I need. So what I do now, I kind of mirror it. So I connect also to 8 and 7. And I just copy this edge pattern to all the nodes in the graph. So I copy this to vertex 2, vertex 3, 4, 5, 6, 7, 8, and 9. And I end up with this graph. So it's still random, but it's much more structured than Erdős-Rényi graph. And in particular, you can see that to generate a Erdős-Rényi graph on 9 vertices, before we had to use 32 random bits because it's between all pairs of nodes. And here we just had to use 4 random bits to same graph. So why it's called also circulant? Because if I look at the adjacency matrix of the graph, then this is a circulant matrix, meaning that I can just take the first row of the matrix and I can just shift it by 1 and populate the whole matrix. Okay, so let's come back to the independence number. So I said that independence number is hard to compute, but how can we actually compute it? So we can take some independent sets. For example, here I have cycle on 5 vertices, and I pick 1 and 3 as an independent set. And I can write a characteristic vector for this set, which is the ith entry is 1 if and only if the ith node belongs to the set. So here the first and the third entry are 1. And I can compute the outer product of this vector, matrix A, which has this 5 by 5 matrix with this structure. So what do I know about this matrix? First, I know that ijth entry is the product of ijth entry of the vector. And if S is independent set, then it is 0 whenever I is connected to J. Just because by definition of independent set, if there is an edge between I and J, then at most one of them can belong to the set. Okay, the second property, if I sum up over all the entries of this matrix, in this case I get 4. And in general, this is the cardinality of S squared. And if I look at the diagonal, I get the trace, which is, in this case, 2, and in general, cardinality of S. And I want to maximize the cardinality of S. I want to find the largest independent set. So I can write this as a following optimization problem. So independence number of the graph is the maximization over all matrices A of the sum over all the entries, subject to the 3 constraints that we saw before. So first, the ijth entry is 0 whenever there is an edge between I and J. Then for the normalization, for the scaling, the trace should be 1. And lastly, the A should be the outer product of some 0, 1 vector V. This is exactly I just take from the previous slide, my construction, and say I want to maximize this cardinality of S. Okay, but this is a non-convex optimization problem. It's NP hard to solve because exactly because of the last constraint, because it's the rank bound constraint, which makes this problem non-convex. So what Lovasz suggested is to drop this constraint and to consider the relaxation of this independence number, which is now called Lovasz number or theta number. And so what do we know? It's the relaxation of the maximization problem, so for sure the value is at least as large as the independence number. And second, this theta number can be efficiently computable by the tools in semi-definite programming. And I believe this is one of the first examples of semi-definite program, which now are prevalent in mathematics optimization. So it's a way to relax non-convex problems. All right, so Lovasz number are very well studied. So it has very nice properties. For example, it bounds some NP-hard quantities. So we already saw that it upper bounds the independence number. It also lower bounds the chromatic number of the graph, which is another classical NP-hard quantity. So the Lovasz actually introduced it not as to upper bound the independence number, but to upper bound another quantity, which is the Shannon capacity of the graph. So it comes from connecting to coding theory. It's if you take a graph and each node corresponds to some letter, and you ask how many messages you can transmit using this code, where you can actually mix two letters if they are connected by an edge. It's like, if you have some graph, how well can you use it to transfer some messages as a coding strategy? So the Shannon capacity is actually, it's not known how to compute it in general. Like there's no formula, even inefficient. But Lovasz number is a quantity which upper bounds it. So Banks, Kleinberg, and Moore use it to study k-colorability of random graphs. Also, Maxina, Mixon, and Partial, and Kuniski use it to upper bound the independence number of Paley graph, which I said before. But in general, Lovasz number is like it's the first step in the sum of squares hierarchy. So because of this, it's very well studied. All right. So what do we actually know? So for the Erdős-Schrödinger graph, it's known that the Lovasz number lies in this interval. So it's between the expected value of the Lovasz number is between square root n and 2 square root n. For the Paley graph on the right, it is very simple to show it exactly square root n, but there are still like many conjectures about some subgraphs of Paley graph, how it behaves. And so our contribution is in the middle. So we study for the random circulant graph. And this is the main theorem, so that we show that there exists some constant such that for random circulant graphs, the expected value is lies between square root n and constant times square root n log n. Okay, so the next I'll show the sketch of the proof for this. So first of all, the lower bound is quite easy. So first, there is a property that the Lovasz number times the Lovasz number of the complement is always at least n. And for our random graph model, the complement of the graph has the same distribution as the graph itself. So we can immediately prove the lower bound by just writing first the log n as the log of the substituting n with the product of the Lovasz number. Then we can use the linearity of expectation and the fact that G complement has the same distribution as G. So we get just twice expected value of the log. And then we use the Jensen inequality to swap the log and expected value to arrive at 2 log expected value. So if you now look from where we start and where we end, after exponentiating, we get immediately that the required lower bound. Okay, so the tricky part is to show the upper bound. And for this, there will be several steps. First, actually, for our random graph model, I told you that the Lovasz number is the semi-definite program, but in this case, it's not needed. Because of the symmetries in the problem, it's enough to actually consider just a linear program. And that's the first stage we'll do. So this is the program as before. What can we notice about this? So first, we can pick an optimal solution A, and we can consider this permutation matrix and look at sort of circulation of this matrix A. So we look at C transpose AC, And the claim is it's also a feasible solution, and it actually has the same objective value. So why is this? Because I take my matrix, so this matrix A, and what this operation C transpose AC is doing is taking each element and just shifting it one on its own diagonal. So for the diagonal, it just shifts them like this, and off diagonal it also shifts by one, while this element goes to here. So on each corresponding diagonal, we just shift the elements by one. So this does not change the objective value because the sum of all the entries stays the same. This does not change the eigenvalues, so the matrix is still positive semi-definite. Now, the last constraint, the trace, clearly is also the same because I just shifted the diagonal. But now the constraint that the ijth entry is 0 whenever there is an edge. For this, it's really important that the graph is indeed circulant because I do not mix the 0 and non-zero element of the matrix A because the 0 element, they just lie on these diagonals by definition of circulant graph. And so it stays, like this constraint is not violated. So it stays feasible. Okay, cool. So what this means is that if I consider this, this matrix A, which for example for this graph, for this cycle, there are zeros whenever there is an edge. But now I can do this operation of circulation, and I can repeat this 5 times. So, and then I average over all the circulations. So then instead of having 10 optimization parameters, I just end up with 2. For example, this A on the right is just the average over all values on the diagonal. So because I do, like after this operation, each element will just walk over the whole diagonal, and once I average, I get the same element on all diagonals. What this means is that I can, for example, I can visualize this this program, but first I can write this as a linear program. So now instead of optimizing over the matrix A, I can just optimize over the vector X. The objective before it was the sum over all the elements. Here is the sum of the elements of the vector, and the 3 constraints that I had before on the left, they just transfer to this constraint on the right, because the constraint that A is PSD is just that the Fourier transform of the vector X is entry-wise non-negative, because the eigenvalues of circulant matrix are just the Fourier transform of the first row of the matrix. And then the fact that the element is 0 whenever there is an edge is just transfers to the element of the vector is 0, and the trace is just the first element. So instead of optimizing over the whole matrix, I just optimize over the first row of the matrix. So this is now X. So this matrix F is the discrete Fourier transform matrix. All right, so what I can do, I can visualize it. For example, this is visualization in 3 dimensions. So here what I'm looking at is the hyperplane, which is the objective, the sum over all the entries. And this polyhedron is the feasible set of solutions. And this is a random set, like this funky looking set, because this second constraint that xj is 0 whenever I is adjacent to j, this is a random constraint. So I have some certain structure like this. So from now on, I can just think of this linear program and deal with it. Okay, so next step is if we want to, remember we want to upper bound the program, and we have this formulation in terms of maximization. Like for linear program, I can just look at the dual program and finding, it seems much easier to upper bound the minimization problem. So this boils down to, this is one of the dual program we can consider. So it's minimization over the vector t. And I want to minimize the first coordinate subject to these 2 constraints so that the Fourier transform is entry-wise non-negative. And I fix some of the entries of the vector to -1 whenever, so jth entry is fixed to -1 whenever j is not connected to 1. Okay, let's see what this actually means. So I have this, so this vector t, and I have this matrix F. so the DFT matrix, I know that the sum constraints of some entries of the vector t are fixed to -1, but I'm free to choose remaining entries. So what do I know about F? So F is DFT matrix. In particular, the first column is 1, and the first row is 1, constant 1. And I want this vector to be entry-wise non-negative, so like to be larger than the vector of all ones. Okay, let's look at the first entry. So the first entry is the vector t hit by the just all ones vector, so it's just the sum of all the entries of vector t. And since they're like essentially half of them are fixed to -1, to find to construct a dual solution, it's reasonable to try to fix the other one to +1. It's like a natural candidate for the dual, because the first entry will have like just the sum of this balanced vector, which will be close to 0. Okay. And for now, let's fix the very first entry of this vector to 0. Why? Because this first entry, it always multiplies just a constant 1. So essentially, if I increase this vector, if I increase this entry, I just add some constant offset to all the entries of this vector. So if my goal is to make this vector non-negative, then of course I can just pick the very large entry here, just adding some large constant, and it will be non-negative. But my goal is to minimize this. So my goal is to add here as little as possible. So for now I fix 0, and I want to see what are actually the values I get on this vector. How much do I need to compensate for? So if I take this matrix F, I hit it by this plus or minus vector. Essentially what I get is a Gaussian vector with mean 0 and the covariance n times identity, because the entries here are IID plus or minus 1. And in particular, this implies that when I set this, so I can offset, I can compensate for the smallest entry. So I pick this entry as the mean of my resulting vector ft tilde with a minus sign. But what is the minimum entry of the Gaussian vector? It is, yeah. So this proves that the Lovasz number is at most square root n log n, because the max entry of the Gaussian is scales as square root n log n. And this is short of what I claimed in the beginning. However, I can say that for the Erdős-Rényi graph, this already gives the best upper bound, the best known upper bound to square root n. And this is the reason for this is because again, we pay the price for going from matrices to the vectors, because here we need to compensate for the smallest entry of this Gaussian vector, whereas if we essentially use the same construction for the feasible solution for the Erdős-Rényi graph, we need to compensate for the smallest eigenvalue of the random matrix with plus or minus 1s, which is actually concentrated to square root n. So we get a much better, like, different scale over there. All right, so so when if I look at the solution for this program and I plot the entries, what I get is that the distribution is not exactly 1, but it's like looks like a Gaussian centered around 1 with certain variance. However, like the feasible solution to improve upon this log n bound will have to have some dependencies between them, because if we choose, like here we choose coordinates just exactly 1, I can choose them from some distribution. If I choose them IID from some distribution, I will still arrive at the same problem with extra log n factor. And this was like last month, this was also in a paper by Feige and Greenberg. They tried to improve upon, for the Erdős-Rényi graph, upon this factor 2, and they have the same intuition that you need some more complicated structures. All right, so let's come to the last part. So what did we do so far? We show the lower bound of square root n. So we have this formulation as SDP, which due to symmetries can be reduced to linear program, and then due to duality, we have this formulation. But here we still fall short of this claimed bound. And it seems that finding a feasible solution is hard to improve upon that bound. So what we will do now instead is go back to this maximization formulation and bound it for all feasible x. So yeah, upper bound the max linear program. And then the first step in doing this is to, so here is the program again. So it's the same program as before, but here I just used the change of variables, but it doesn't matter. So here the vector y is f times x as before, but it's exactly as before. So I want to maximize over the vector y, n times the first coordinate, subject to the vector y being non-negative. So the fj is the jth column of f. It needs to be orthogonal to the certain columns of discrete Fourier transform. And the L1 norm is 1. So we have this, here we have a deterministic objective, but a random feasible set. And it seems that it's easier to work with linear programs, with random linear programs, where the objective is also random. So that's the first step we're doing, introducing the randomness into objective. So I can write this n times the first coordinate as the inner product between y and sum over all the columns, f. And then since I have the constraint that the y is orthogonal to certain columns, I can subtract this part. So I can subtract the columns which correspond to k which are adjacent to 1, because the inner product between 1 and fk is 0. And this I arrive at the inner product of y and the vector fb, where b is now a plus or minus 1 vector. So bk is plus 1 if k is not adjacent to 1 and minus 1 otherwise. So now it's a random objective, and the vector is essentially like a Gaussian vector again, as we saw before. All right, so with this, I have this the last linear program that I consider. So now I just change the objective and I look at these two constraints. So it's the max over the y, inner product of y and vector fb, subject to L1 norm being 1, and y lying in some subspace, which is the kernel of matrix f tilde. So f tilde is the subsample DFT. It's the same as saying that y should be orthogonal to certain columns of f. So it belongs to the kernel of this matrix. So and I'm interested in expected value of this program. So if I see that fb is a Gaussian vector, essentially this is like close to the Gaussian width of this feasible set of solutions. And the Gaussian width of like L1 ball is well studied, and in general it seems promising. So what I have here, I have the L1 ball constraint, which is shown in orange, and I have this subspace constraint, which is shown in blue. And so L1 ball in high dimensions looks like this spiky object with some very sparse vectors having large L2 norm, but the majority of samples having small L2 norm. And so these vectors which have large L2 norm, they will really increase our objective, our inner product between y and fb. So we want to get rid of them. And the second constraint, that the y belongs to the subspace, this random subspace, allows us to do this. So intuitively, if you look at the picture, at the intersection we have points, we have dense vectors for which the L2 norm is much smaller than L1 norm. So this subspace kind of cuts off all the spikes of the L1 ball. Yeah, but how, like, okay, they are dense, but this subspace is not just a uniformly random subspace. It's a subspace from the subsample DFT. So it's like the last question we need to answer is how dense these vectors indeed are. And so this ratio between L2 norm and L1 norm of the vectors for vectors in the kernel can be controlled by a restricted isometry property of the matrix F. And so for the subsampled DFT, this is well studied. In particular, it's known that we have the bound that L2 norm is at most L1 norm over square root n up to this log squared factor. in a series of work in the past 2 decades. Yeah, so informally this means that there are no very sparse vectors, so no n over log to power 4, for example, sparse vectors. However, we cannot remove this. We still need some log in the denominator. If it would indeed be like just a uniformly random subspace, then this would be true just up to some with some constant instead of log squared. So it would be a stronger result. But since our subspace is not uniformly random, but it's some subsampled DFT, we need to pay these log terms. But it's enough to show the bound up to this. So with these extra log factors. So this log exactly comes from the fact that we're dealing with this subspace. All right, so to conclude, so we proved this upper and lower bounds on the Lovasz number, so improving upon the simple feasible solution. We conjecture from the numerics that the lower bound is tight, that it should be exactly square root n with the factor 1. And the same conjecture also holds for the Erdős-Rényi graph. So you can check on the computer that it behaves constrains a lot around square root n. Of course, on the computer, it's hard to check whether it's indeed a constant or it's like a log factor. But okay, it's like looks exactly like square root n with the factor 1, so we can make this conjecture. There is one constraint, one condition that I removed at the end, so that the y should be non-negative, which should help us to bound the program more. And so pictorially on this here we kind of only look at one quadrant of entry-wise positive vectors, which should further restrict the maximization problem. But it's not clear how to use this constraint for this program. So it's still interesting to look at what is the good feasible solution, what is the construction for the good feasible solution for the dual. So this simple construction is not satisfying. And lastly, I did not talk at all about the concentration, but this, again, empirically, this theta number concentrates a lot. And but the techniques, they fall short to prove this concentration because in this problem there is essentially no locality in the graph. So if I remove, usually how we prove, one way to prove the concentration is say I have my program depends on a lot of randomness. I look what is the effect of one random bit. So what is the effect of adding or removing one edge in the graph? But for the random circulant graph, I cannot just add or remove one edge. I need to remove the whole n edges in the graph. So this affects a lot. This complicates the analysis of the concentration. Okay, just to end, I would say that our group, we have a blog on the internet where we write about open problems. So about this one in particular and others. So feel free to check it out. Thank you for your attention.
Thank you, Danny. Very clear and interesting talk. Any questions? Yeah.
Great talk. So up to this positivity constraint, your question is just exactly equivalent to RIP of subsampled Fourier transform, right?
Yeah, if you remove a positivity constraint, then yes. But exactly, yeah. But and then yeah, thanks. So there's a lower bounds for the RIP of subsampled DFT, which basically show that this. So I said that there are no n over log to the 4 sparse vectors, but there are n to the log sparse vectors in the subsampled DFT. So yeah, exactly. So that this log factor will be required there.
Right. Other quick question. So you didn't say much about the clique number itself of the random circulant graph. Is that understood?
Yeah. Thanks. Yes. So the clique number is understood. So it is of order. It's basically up to constant log n. And actually, in some cases, I think for prime, when n is prime, then it's exactly 2 log n. So it matches exactly the Erdős-Rényi, the clique number for Erdős-Rényi graph. Yeah.
I had one more question, but I'm happy to ask it after other people ask.
You have the mic.
Yeah, okay.
The reduction from the STP to the linear program sort of seemed general, right? Whenever this thing has a symmetry, I guess you're taking the representation of the symmetry group or whatever, and then I mean that's where the Fourier transform came up.
Exactly,
As a
exactly.
representation. So how general can you make this thing for like other random graph models?
Exactly. Yes. Thanks. So. Exactly. So, I mean, random circulant graph is a special example of random Cayley graphs over the group. And the group here is a cyclic group Zn. Here we just need that the group is abelian, commutative. And then, as you say, because of the same symmetries, it will go through. But exactly because the RIP of other like binary Fourier transform is also studied. Yeah.
I saw another hand there. Okay, so is there any other question? All right, if there is no other one, let's thank Daniil again.